Good evening and very welcome to the University of Aberdeen R.V. Jones lecture. My name is Marian Wiercigoch. I'm the convener of this lecture series. 2020 has been unprecedented and very challenging. We hope that this pandemic experience will result in positive changes for the society at large and our planet. Along these lines, we have a stellar speaker planned for tonight, Professor Sir Jim McDonald, who will share with us his views. Before we start, a few housekeeping points. There's no chat facility, so please only use a question and answer section for questions. Questions can be submitted during the lecture, but will be answered during the question and answer session. Can you please add your name and affiliation to the question? Questions are moderated and will not show instantly. Duplicated questions won't be published, but will be responded after the event. Question can be liked by the attendees, so you can put your like mark. So what will happen next? Next, the principal will briefly introduce the R.V. Jones series and the speaker. Then we will have the lecture, which will last approximately 50 minutes. Then we have a question and answer session, around 15 to 20 minutes. And then the head of engineering will close the event. Can I ask now the principal and the Vice-Chancellor of the University of Aberdeen, Professor George Boyne, to extend his welcome and introduce the R.V. Jones series and the speaker.
Thanks, Marian, and good evening to everyone in this impressively large audience. It's my great pleasure to give the opening remarks and introduction for this evening's event. The R.V. Jones Lecture is an annual series of lectures by distinguished engineers and scientists, which is named after Reginald Victor Jones, a British scientist and military intelligence expert who played a critical role in the defence of Britain during the Second World War. First, a few words about R.V. Jones and his time at the University of Aberdeen. After the Second World War, R.V. Jones's wartime colleague, Professor Edward Wright, who later became principal here, suggested that he should apply for the university's chair of natural philosophy. R.V. Jones was offered this role in 1946 and held it until his retirement in 1981, a mark not only of scientific achievement, imagine perseverance and a great deal of tolerance. During his time at Aberdeen, much of Professor Jones's attention was devoted to research to improve the sensitivity of scientific instruments, such as seismometers and optical levers. Next, I'm pleased to say that we have a very special guest attending the lecture this evening. I'm delighted that Rosemary Forsyth, Professor Jones's daughter, has joined us as guest of honour. Rosemary, I can't see you, but I hope you can see us and will enjoy this evening's lecture. It's a super pleasure to have you here with us. Now to our distinguished speaker this evening. Professor Sir Jim McDonald is Principal and Vice-Chancellor of the University of Strathclyde and is one of Scotland's most accomplished engineers. He co-chairs with the First Minister of Scotland the Scottish Government's Energy Advisory Board. In the Queen's Jubilee Birthday Honours List in 2012, he was awarded a knighthood for services to education, engineering and the economy. He was elected President of the Royal Academy of Engineering in September 2019 and is a member of the UK Prime Minister's Council for Science and Technology. Jim holds many prestigious fellowships. He is a Fellow of the Royal Academy of Engineering, the Royal Society of Edinburgh, the Institution of Engineering and Technology, the Institute of Physics, and the Energy Institute. He is also a Foreign Fellow of the Chinese Society of Electrical Engineering, an Honorary Professor at Peking University, and a Guest Professor at Nankai University. Professor McDonald's lecture this evening will contextualise the drive for low-carbon energy systems by providing a brief history of UK energy system development and highlighting key low-carbon technologies as we look to our energy future. This is a crucial topic for the northeast of Scotland as we look to a post-pandemic economic recovery that is truly sustainable. Energy transition is also a key research theme for the University of Aberdeen and is one of the 5 interdisciplinary themes in our Aberdeen 2040 strategy. Colleagues, students and guests, it is my great pleasure to introduce Professor Sir Jim McDonald.
Thank you very much indeed, George, for that generous welcome. It's a genuine privilege for me to be delivering the R.V. Jones lecture this evening. One, first and foremost, because of the enormous respect I have for the University of Aberdeen, one of our ancients, and been led wonderfully well by Professor Boyne. So it's great to be here with you this evening. And a particular pleasure for me to know that Rosemary is also in the audience, and I will do my very best to uphold the expectations of Professor Jones in terms of contribution to understanding and discourse. So with that, colleagues, let me begin the lecture. I'm going to take you into a whirlwind tour of energy, and probably a recurring theme that I will come back to this evening is energy systems. As George has mentioned, I will touch on specific low carbon technologies, be that in wind, energy storage, whether it's in electric vehicles, but increasingly we have to understand that these things have to be integrated together to create the energy systems of the future. And as you'll see from my opening slide, the sub-theme is about decentralisation, decarbonising, digitising and the democratisation, which I'll come back to later. So I'll go to my next slide, thank you. So let me give you some broad brush where we are in terms of the current policy. Let me start at the 12 o'clock mark on this slide. There are very senior energy policy commitments that have been made internationally. In the UK, we have the United Kingdom as one of the largest countries that have made a legally binding commitment to net zero by 2050. And with the Scottish Government has made a similar commitment to 2045 and driving decarbonisation, such as getting rid of internal combustion engines being sold and brought onto our roads by around 2030. And Scotland, although a small country, genuinely, to use a cliche, but it's true here, punches above its weight in terms of our thinking, our innovation and the talent that we produced. Continuing clockwise, there is undoubtedly a growing social conscience, and this is helpful, not least of which from our wonderful young people and our students at our universities, indeed in schools as well, as they are awakening to the need to be addressing climate change, and that accountability and awareness will be driving the political classes to make the right decisions. And lots of technologies are pushing forward here. We have a very secure and well understood offshore and onshore wind industry. These are now cost competitive, highly effective in terms of electricity production. Digital technology is required to create the flexible and responsive energy systems of the future, and activities such as power electronics allow us to redefine the grid, which I'll come back to later on, as well as all the comms, sensing and intelligence we need to integrate and operate large systems. And energy systems I've mentioned down at the bottom right hand corner, and increasingly this is about the integration of electricity, heating or cooling systems, transport and fuel mix, and seeing this both in a regional dimension and a reconfigurable dimension too. And the drive for sustainable energy, not least of which because of the strategic imperative and quite frankly the vision for the SDGs, these 17 drivers for creating a much better planet that is equitable, that is clean, is sustainable, and driving for me also the development and electrification debate around developing nations. Cities are being recognised as super hubs. Over the next 20 or 30 years, about 80% of the world's population will be in urban environments and will be producing about 80% of the world's pollutants. So we have to see cities as a big area for focus. Cities like Aberdeen, Glasgow, London, of course, and beyond that internationally. And if we think about industrialised nations such as our own, the energy infrastructure is ageing. Whether that's in the oil and gas industry, whether it's the electrical infrastructure that we have, these are ageing assets. And for the past 20 years, I've been talking about the need to reinvest and rewire Britain. Now we have no option. We really have to take a big push and invest what is going to be hundreds of billions of pounds in the UK and in Europe, and trillions in Europe alone over the next 20 years to decarbonise the network. And finally, and last but not least, in spite of the naysayers, the acknowledgement based on the data that's in front of us of climate change and global warming as a reality that we must address as one of the existential questions for the 21st century. Next slide, please. And there'll be a sequence of photographs I want to take through just to capture some of this. So let me just talk about these photographs here for a moment. Top left-hand corner is a hero of mine. This is a Scotsman called Lord Weir, who was commissioned by the UK government in the 1920s to look at how one rolled out electrification in the UK. So the Lord Weir report led to the creation of the Electricity Supply Act in 1926, where they coined the phrase the grid, and he talked about the creation of a national gridiron of electrical connections, which ultimately led to the creation of the Central Electricity Board, and through that the large centralised power stations and beyond, which is really by and large the architecture that we have these days. Roll forward to 1992, the world wakening up to the need to address climate change. This is the Kyoto summit, which really laid out the markers in the international commitment. Go to 2006, and I'm delighted to say that the chap on the left is Nick Stern. He was Sir Nick Stern back then. He's now Lord Nick Stern, an economist at the London School of Economics, but an expert in the economics of climate change. He was commissioned by the then Prime Minister Tony Blair to produce the eponymous Stern report, which I still commend to you all if you can have a look at it 14 years later. It's about the need for innovation, the need for scale and deployment at large scale, addressing deforestation, but decarbonising and creating new industries on the back of creating, an addressing of the climate change. 2006, also, you can see here Al Gore, almost an American president. And we won't go into that one, given the controversy that we're currently seeing in North America. But Al Gore, a great champion for addressing climate change. His movie that had a massive impact on public awareness called The Inconvenient Truth. It was addressing issues that really woke many people up to what we were doing to our planet. And then another COP15, Copenhagen in 2015, and the international panel on climate change, or I should say the intergovernmental panel on climate change, where we had been thinking about 2% reduction in temperature increase, I should say, rather. And what they're saying is really things start to go very wrong at a 1.5 degree increase in the seas around the globe. So let me just have my colleagues sequence through a few photographs. But as we awaken, let's look at the next few slides. The next person that you'll see, you'll be aware, we've got Greta Thunberg here, a young woman who's had a disproportionate impact on global awareness. If we continue, and we can see movements, just continue to sequence these photographs, please. We have, Extinction Rebellion. You can see the photograph here as they've been making their marks felt. Royal Society of Edinburgh just last year published their Scotland's Energy Future, which was looking at this system's architecture and the need to carbonise. The Committee on Climate Change, chaired by a young Scottishman called Chris Stark, who worked in Scottish Government, now is the CEO, I should say, not chair. And it was them that coined this phrase about net zero that has driven much of what's going on out of UK government. And the next plate, if I can, please. Today actually should have been the day that the UK Energy White Paper was published. I think all of what is going on with the Brexit negotiations has probably pushed it into next week. And just last week, I had the pleasure of having a meeting with the Secretary of State, Alex Sharma, who talked quite nicely about a golden thread that will be woven through that energy strategy that will connect where we are now to 2050 and decarbonisation. And a big target for all of us that will put Scotland on the map is the COP26 meeting in November next year, where there hopefully is a real opportunity for the Glasgow Accord to emerge, where we're really getting intergovernmental approaches that will make a difference. So let us continue to the next slide, please. And here is one of the fundamental challenges. Nothing is easy to achieve, but it's better if we understand where the tensions are. And I've got the three tensions here moving in opposite directions. So we all want to decarbonise, that's correct and right and proper as we address climate change, but we also want security of supply and reliability. So we want the lights to stay on. We want to keep our commerce and industry fed with electricity. Increasingly, we'll need that for the electrification of transport. But that reliability and decarbonisation has some tension based on wind and energy storage and dealing with intermittency. And of course, it can't be at any cost. So affordability has to be played in there. So this is what's called euphemistically the energy trilemma. But it's actually even more complicated than that, because public acceptability and public opinion is fundamental here. Unless we as citizens, we as energy consumers, and quite frankly, those that dispose our income, unless we buy into this, it won't happen. So the policy needs to be right. And of course, the other tension, as I mentioned with regard to Nick Stern, is we have to make sure we get a positive impact in the wider economy. And you've heard about building back better, the green industrial revolution. That is fundamental. So these are our tensions. Just keep going, please, Sean. And so we need to look at options. What will they cost? Will they work? So engineering, science and technology, fundamental to this, and the policy and economic levers that need to be in place have to be integrated too. So let's go to the next slide, please. And here are a few things that have been happening recently. This is a rather busy slide, forgive me, because it's been rather busy in this space. So I just put this slide together last night, looking at some recent developments. Only a couple of weeks ago, the Prime Minister published his 10-point plan for a green industrial revolution. And I've given you the headlines there. And these are eye-watering targets, let me tell you, given this is only to be done in the next 10 years. So offshore wind, Mr. Johnson said he wanted all domestic energy to be supplied by offshore green energy. Now that means deploying 4 times the current amount of offshore wind that we have, or 40 gigawatts by 2030. Hydrogen will be a key part of this, and looking for 5 gigawatts level of production by 2030. Nuclear is back on the agenda. I have not seen yet the energy white paper. It will be published next week, but I am expecting fully there'll be a commitment to advanced modular reactors and small modular reactors by 2030. Rolls-Royce has already made a commitment to have somewhere between 5 and 10 of these devices ready by 2029-30, of the order of about 400 megawatts each. The typical large-scale nuclear stations are about the gigawatt capacity, but this is another contribution to low carbon, notwithstanding fuel storage and the legacy there. Electric vehicles, public transport. Remember, it's not just about technology, it's about how we live, how we use systems. And I will come back later on to try and define what we mean by jet zero, not just net zero, but decarbonising the aero aviation industry and green maritime, and so on and so forth. And when I say carbon capture, a big opportunity for Aberdeen in the northeast in partnership with the oil and gas industry and other companies. Negative emissions, we should be planting 30,000 hectares of trees every year to try and mitigate the effects of CO2. The middle tranche is important as well. You heard from George. I have the privilege of sitting on the PM's Council for Science and Technology, and in January this year we sent a letter, because that's how we communicate with the Cabinet Office. It's not quite as prosaic as that, it's backed up with serious reports, promoting the need to achieve net zero by using a whole systems approach. And we need that by integrating government department approaches, whether it's in economy, whether it's in industry, whether it's in the Ministry of Communities, Local Government and Housing. There has to be a joined up approach. There isn't currently, but there is an intention to do this. And this will also mean working with devolved governments and city governments to get that flow through from big policy commitments to delivery. And that also means better aligned regulation so that this is facilitated. And we need the analytical and modelling capability. If we are going to solve this through good technology, good science, good innovation, we need to be able to model where we're getting to, and I'll come on to that in a moment. And let's maximise the use of technology and the investability of what we're going to do. The energy systems catapult, and catapults are one of the UK government's instruments to encourage innovation. One such is the Energy Systems Catapult, published a very good report in April this year. Again, I would commend that to you. Look at the catapult in energy systems there, 2050 scenarios for net zero. They'd already been modelling for an 80% reduction in CO2 by 2050, when the Committee on Climate Change pushed out the idea of net zero. They revised the models, and what's come out is perhaps not terribly surprising. There's a 2 to 3 times multiple potentially on the electricity we'll need to generate. Part of that will be, of course, nuclear and bioenergy combined with carbon capture and storage, whether that's biomass gasification with CCS, renewables and decentralisation, negative emissions, some exciting opportunities technologically with direct air capture, where we can use either liquid means or solid means to absorb CO2 from airflow, and then chemically remove and potentially deep mine, store the CO2, or potentially use it as we go to CCUS, carbon capture, utilisation and storage, using it for food production or using it in industrial processes. But the last one I'll point out again, demand side behaviours are important. How we use energy, how we live, and of course, COVID-19, thankfully we're seeing some light at the end of the tunnel. I think will be seen as one of the biggest drivers for digital transformation and indeed decarbonisation that we've seen so far. And I had a very nice way of that being put just a couple of weeks ago when an economist friend of mine said that COVID has shown that we can decouple productivity from carbon emissions. And we're doing that just tonight as we use this digital platform. Okay, Sean, next please. Let's look at the next slide. So let me give you a broad perspective here. This is by and large the large-scale power stations in and around the UK. You can see Peterhead. Yeah. Peterhead's close to my heart, by the way. When I was a young engineer, 1979, 1980, I worked up there in the commissioning team as we built that. Lived in Bodham Harbour, and I got a treat to come down to Aberdeen on a Friday and Saturday. So that station is still going, converted originally from oil to gas, and you can see the nuclear stations all the way through. But if Sean, next slide, you can see what happens in the next 5 years. That's what the large-scale power stations are going to look like in the UK, and some of those might be time limited as well. So you can see there's a real issue not only about ageing infrastructure, but the assets are going to come off their useful life. So just as we need to ramp up sources of electrical generation, the fleet and the infrastructure is aging. So we've got a real cleft stick here between aging infrastructure and the need to electrify. Okay, next slide, please. And here's a national grid plate. So forgive me, it's a bit cartoonish, but just to give you the end of it, on the x-axis, we're seeing the speed of decarbonisation over the next 30 years, and on the y-axis, we're seeing the level of decentralisation to achieve it. So the yellow box shows if we simply make steady progression, yes, we'll have more wind. We'll be dealing with things like more efficient boilers and heat in homes, and we might decarbonise in factories. But that will be steady progress, which will not get us to net zero. If I go to the blue box, consumer evolution, where we're getting much more consumer engagement, or the cliche is that consumers become prosumers, where we've got building integrated renewables such as solar. We might have geothermal, and ground source heat pumps, air source heat pumps, and the likes onto the grid. That moves us further on decentralisation, but not to the targets. Where we should be aiming at is the right-hand side of this graph. So the green box is being driven by the 2-degree increase in global temperatures, or the IPCC tell us it's 1.5, and that needs lots more renewables. It needs a much bigger effect on built environment to reduce energy requirements, and electrification on transport. And if we go to the top right-hand corner, you're seeing an amalgam of this, where we've got standalone, decentralised systems that can be reconfigured as required, and wholesale electrification of transport. So that's a cartoon version of where we need to go to. Let's have a look at the next slide. Here's a traditional power system that you'll recognise. It's again a pictorial simplified example. In the top left there, You've got the large centralised generation stations such as Lord Weir imagined 94 years ago, and that comes through step because of AC, because as we know, Nikola Tesla, backed by Westinghouse, won the arguments about AC versus DC. We can transform that up into transmission level voltages, 400 kV and beyond, and then step down again to distribution to homes, commercial and industrial applications. But as we move forward now, there's much more active use of the network. Next slide, please. And you'll see here, there's a much more integrated basis for generation. So we've got integrated solar and energy storage, whether it's battery or fuel cells. We've got wind in and out around the communities, not just in the remote levels. Of course, we have big wind farms and the likes there, and all the way through to grid integration. So in many ways, we're inverting the system from less dependency on large-scale generation to much more integration and use of distributed energy. So this is a plate that came out of a European project on smart grid 2000. So next slide, please. Now you're getting this from an electrical engineer, so I'm letting you know about the grids. We'll be moving on to other technologies. So let's, Sean, just hold it there. I just want to build this plate. So what you're seeing here is in 2000, this family bicycle ride is emulating what the power system looks like. The adults there are the large power stations, the coal stations, the gas stations, nuclear, and the kids are the smaller ones like hydro or combined cycle gas turbine. Today, Sean, if we just go to the middle rank, here's what the system looks like. Here's mum and dad, and press again. So mum and dad are the large power stations, nuclear or large coal or gas, although we're phasing out coal. And the youngster is a distributed generation system. So just press that next button. So the youngster is here a solar farm coupled with wind. As we move forward over the next decade, thanks, Sean, instead of the adults being prevalent, we're going to have more and more and more of these small-scale stations driving a whole system. But note, I'm showing these tandems or these multiple tandems. They are interconnected. Each is depending on the other to be synchronized in order to drive the system. And another key push, thanks, Sean. And the key here is low carbon network innovation is essential. Only last week, Deputy President of the European Commission, Immerman, stated publicly that the European Green Deal will only be delivered if there's wholesale investment in decarbonising and revolutionising the grid in Europe. So it's not just the grid, but it's not just the sources and the end uses. So it was good for me to hear as an electrical engineer, this recognition is there's a wholesale evolution required to create smart grid and to be ready to combine and integrate these low carbon sources. So let me show you a video now, which demonstrates the need for innovation. Thanks, Sean. And you'll see this chap here represents the small scale generators. He's about to innovate to catch up with and overtake, hopefully, the current large-scale generators. And I'll just give you a few seconds. So here we have it. Well, that's wind farms, whether it's solar, whether it's battery storage. He's overtaking them. He's about to catch up with some of the bigger systems as well. I won't overplay this analogy, but I'd like you just to see with a smile what happens when he overtakes the final conventional system. So he's now overtaking by applying innovation and, quite frankly, taking a bit of a risk, but hopefully in a managed way. About to overtake the leader here, and now he's catching up with the, let's say, an equivalent of a large-scale conventional thermal station. And you'll see the effect that he's had on them. And so it goes. Anyway, a bit of fun, but to give you an idea that we need innovation and we need to keep driving and challenging the model. Thanks, Sean. If we move on to the next slide. So the network will evolve. Here we see something that's important to Aberdeen in terms of its opportunity for low carbon energy, translation from the oil and gas industry and the energy transition. We've got offshore wind here. We've got a transmission network that needs to evolve. You should know that we have a Western link just now, which is a 2 gigawatt subsea DC link from Scotland down to the northwest of England. and work is now underway between Scottish Power, Scottish and Southern Energy and National Grid to consider an Eastern link and do the working and the modelling of what that might look like, which would definitely take in the North Sea oil fields, the offshore wind potential, and there would definitely be connections in and around the Aberdeen coastline for that grid. And you see lots of energy consuming devices in the right hand corner and an ageing distribution network therein. Sean, just cycle through that, thank you. And it's going to be a mixture now of AC, DC generation. And this slide will tell you, again, just have a look at some of these numbers. There's going to be a massive increase in the need for us to control, monitor and manage generation. So I used to work in the utility industry. Then you were managing a few scores of large generating stations. Now, today we've got about 10 to 15 very large units. By 2030, there'll be over 500,000 generation units will have to be to some extent coordinated, scheduled, managed and kept integrated to maintain voltage and frequency limits. We're going to have a critical need for ICT infrastructure, whether that's pervasive communications, 5G comms, optical comms, distributed intelligence, getting intelligent agents out there onto the system so there's a degree of distributed coordination. And ultimately, we'll be looking at pushing out the generation opportunity into homes and into communities, as well as maintaining large grid level generation. Okay, thanks, Sean. So just one brief slide. So one way to do this, and I won't drop you into the detail of this, is a significant European project that's been worked on just now, which is called the Web of Cells, which is saying the Lord Weir model, which is still absolutely correct, of having large-scale grid integration, has to be complemented now by strategically potentially decomposing the network into autonomous units. So here you can see there can be high voltage cells, medium voltage cells at the 11 kV, 33 kV level, all the way down to LV and in our homes. And so that's going to require for us to challenge the current standards, look at how the industry works. And now is the time. And there are lots of very nice pieces of work that are focusing the industry in that direction. Thanks, Sean. So just before we go into low carbon generation, let me give you a couple of analogies, because this decarbonisation is a whole phase wavefront of change. So in Mr. Johnson's announcement a couple of weeks ago, he talked about jet zero and greener maritime. And let me just give you an idea of what that means. So there's a technological and strategic and environmental convergence that's going on in the systems that we're used to, the generators, the transmission systems, the loads that we use. And the same is happening in the aviation industry and the maritime industry. And the drivers are the same. Distribute electrical energy systems, decarbonise and reduce environmental impact, because there's a very big proportion of the world's emissions is produced by ships traversing the oceans. And there's a big push from the regulator to try and decarbonise the emissions from aircraft as well. And a lot of that will be driven by digitisation. So you're seeing a picture emerging here. So let me go into the next couple of slides. Thanks, Sean. And here is a model of on the left-hand side. Here's a traditional Boeing aircraft. It does have quite a lot of electrical generation on it. You'll see on the engine, there's a 120 kVA generator that's mirrored in the other wing, and that's distributed through lots of cabling. Lots of this is hotel load, of course, your entertainment, the electrification of your seats, the lighting, the air conditioning, and the loads are distributed. On the right-hand side, you can see how these aircraft have evolved even into the 787, where if you look on the engine, there's now 0.5 megawatt of electrical power coming off of these Aero engines themselves. So as well as thrust for flight, we're deriving about half, in fact, in total across the two wings, 1 megawatt of electrical power. And that allows us, rather than distribute power hydraulically, which is some issues, you need duplicate and triplicate safety activities, but the electrical distribution reduces weight and it allows you to manage electrical power so much better. Let's have a look at the next slide, please. And here is a concept aircraft, and it's only that just now, driven by NASA, but we need these far out ideas. That's why research and innovation and really smart students and researchers can make a difference. Here is the TED-P concept of the turbo electric distributed propulsion. if you look at the numbers, 16 3-megawatt generators on that wing design. So we're talking about 50 megawatts approximately of electrical drive. Now, we still have to think about the fuels that are being used, synthetic fuels, hydrogen-based, where we use energy storage. But along here, it's about high efficiency, radical redesign of civilian aircraft. And this is a concept that's being modelled. It's not flying yet, obviously, but every aircraft starts its journey on a computer screen these days. Then we have to build up through prototyping. Thanks, Sean. Next slide. And here is a very interesting, this project has been paused just now, a fantastic I hold the Rolls-Royce chair in electrical systems, so my old research group at Strathclyde have had inputs to the electrical design for this aircraft. This is the eFan-X concept, which had electrical generators working with Rolls-Royce, Siemens and Airbus. Again, have a look at the wings, colleagues, and you'll see that in each of these fans, these Aero engines, there's a 2-megawatt motor. So along that wing, there are two 2-megawatt motors. So 8 megawatts across the wing, and all of those have been driven and controlled, but just the same way as land-based systems have been controlled. Power electronics, advanced controls, distributing the electrical energy, and this was a proposition to move towards, rather than a more electric aircraft, an all-electric aircraft carrying about 100 people for mid-range flights. So these designs will come back, and they'll come back at pace, mainly because of the need for the aviation industry to respond to the regulator's requirement for getting emissions controlled. Thanks, Sean. So let's think about that model again. This is that was jet zero. This is maritime greening. So you've got everything from naval craft here, submarines, all the way through to the engines that drive it, and the naval fleet. Thanks, Sean. Next slide. And the idea here is, bear this in mind, which is maybe surprising for some of you. These large cruise ships, sort of Caribbean cruise lines, that 91,000 ton ship has got about 40 megawatts of electrical generation on board. So for me, as a simple electrical engineer, that's a floating electrical system. And if you look at the naval craft in the bottom left-hand corner, much more manoeuvrable, it's smaller. It's also got 40 megawatts, but that's about manoeuvrability, survivability under battle conditions. That's high power, high density, and the one at the top is high power, low density. But the next slide, again, I won't stick on, that the electrical system that describes a distributed generation system on land or on an aircraft or on a ship looks very similar to me. It's generation sources, it's energy transformation through either AC/DC translation, or it's transformers to move the voltages about, power electronics to control, and then moving it on to efficient drives. So all up, the whole journey of electrification is underway, and the driver is predominantly environmental management and addressing climate change. Okay, thank you, Sean. So let's think about wind now. The Aberdeen Harbour is already a great test site for floating wind, which we'll come on to. The vision that Sir Ian Wood and colleagues have for the energy transition zone up there about manufacturing advanced devices. Have this picture in mind in the long term. You can, if you just, sorry, Sean, just back up if you don't mind. Staying on this one for a second, you can see the evolution of the scale of wind generators. So 30 years ago, talking about 0.5 megawatt, and as we transition now to 2020 and beyond, we're talking about wind turbines, predominantly offshore wind for this scale, of up to 12 megawatts and above. And if you look at the measurements here, the rotor diameter on these devices at 220 meters, and from sea level upwards, you're talking about sea level to blade tip at the top, over 300 meters. So from an engineering point of view, a spectacularly attractive proposition. Advanced materials, design and control, the electromechanical integration, the control ability of this. And the key thing here is that, and this number is going up every year, there's an estimate of over £2.5 trillion worth of investment required in wind energy globally, but I can assure you that number is going to increase given the international commitment to having more wind, particularly offshore. And the numbers I've put there about needing 4,000 turbines by 2030, that number is up, and it'll be north of 5,000 large-scale offshore wind turbines if we're going to achieve one of the 10-point plan targets from the Prime Minister. Okay, Sean. Here's some rather exotic designs. So floating wind, Equinor, that I'll mention shortly. Great pioneer up here in Aberdeen. Sorry, up there in Aberdeen. The opportunity to pioneer the next generation of large-scale floating wind turbines. Great engineering and design required. This is a proposition where the devices are autonomous. It's being monitored and managed by drones. Battery storage alongside it, moving along to the kite-driven offshore. Some fantastically innovative designs. Those of you that are interested in browsing, have a look at the Makani device, M-A-K-A-N-I, a Norwegian company. Quite far out there. It's a proof of concept just now, where they've got offshore a device. It's actually like an upturned aircraft in cruciform, and off it goes, tethered to an offshore location, and it derives and it harvests wind, brings it back to a collection point, and then on shore. Some very exotic designs, such as multiple rotor turbines, and at the end there you can see potentially very large vertical axis devices again, which can be made autonomous and managed there. And that's where I should say there's an awful lot to be learned from the oil and gas industry in terms of managing safely and effectively offshore assets and building an industry around it. Okay, Sean. Here we have it, just off Peterhead, the 5-6 megawatt floating spars have been in there in 2017. Large scale, learning a lot about the engineering, the installation and the operation. World's first floating wind array. Keep going, please. And we can see just a build here that from floating wind from 2003 to 2018, that was great. And over 15 years, we can see the next section. Here is the reality. And the next button press, please. We can see here the head of Equinor saying that floating wind could outcompete bottom fixed by 2030. And that's happening now at pace. And I may say, and there are colleagues and friends of mine in this call who are deep into this industry of making this argument for floating wind for a long time. And the offshore renewable energy catapult that I mentioned it will hopefully be at the heart of that and driving economic benefit for Scotland. Because let me look back again, what Nick Stern said 14 years ago. Let's address climate change. Let's build low carbon industries. Let's decarbonise energy supply, but let's create jobs and economic opportunity as we go. And floating wind is one example of that. So next slide, please. And lots of the innovation is multiple. We've got the European Marine Energy Centre up in Orkney. That we're now seeing, Wave, of course, still a challenge, but the good IP and good engineering in Scotland, and Tidal opportunities. So it's now about scaling here from a few hundred kilowatts to megawatts. There's some really good designs here. Rising air columns. Next slide, please. That's the Ocean Energy Buoy in Ireland. The next one here. This is Atlantis and Lockheed Martin. And for me as an engineer, I'm starting to see some design convergence here, which showing, that we're moving towards the commercialisation stage of these devices of a few megawatts anchored to the bottom and then with a power takeoff. And Scotland, again, playing a very important role in that late stage R&D demonstration stage, which hopefully not only innovates, but attracts companies in to get access to the talent out of our universities and companies, but also stays here and makes the devices as we try and make this industry work. And again, the offshore renewable energy catapult has a role to play here in accelerating these industries. Thanks, Sean. So just before I go to my next video, and there'll be a voiceover here, innovation isn't just done by big companies. Of course it's done by them. Of course it's done by researchers in university labs. And that will continue and has to be funded well, and we understand that. But I would commend small companies such as Marin here, that I'm going to show you their video, where they have a vision for the future. This is a maritime consultancy based out of Holland, but I know the CEO, and when he shared me this video, I was absolutely bowled over, because here's a relatively small company with a big vision, and we need big vision, great technological innovation, policy levers to create the future. And here's a version of Marin's future that Sean will now show you.
The wind and the sun represent a massive source of renewable energy, which is more abundant at sea than on land. Harvesting this energy will require offshore wind parks and floating solar panels, as well as wave energy converters, tidal turbines, and ocean thermal energy conversion. Processes are being developed to store the vast amount of renewable energy efficiently, in the form of hydrogen, liquid methane, or ammonia, for example. The availability of this technology offshore will be a game changer for shipping and harbors, creating entirely new maritime infrastructures. Large-scale wind and solar-powered energy and transshipment hubs will be located along major shipping routes. Small-scale energy production along rivers or in remote areas will also appear, redistributing the energy infrastructure. These energy islands could be used for renewable energy conversion and storage, but also as logistics islands, where cargo could be transferred from larger to smaller ships. Massive technological innovation will be needed if this is to become a reality, representing a true challenge for a number of industries. This energy transition means that communities all over the world will benefit from locally produced and stored renewable energy and environmental sustainability, and will remain connected to each other through zero-emission transport infrastructures. The shift to ocean energy hubs will not only support next-generation shipping, but will also open up the possibility of floating settlements. Rising sea levels in densely populated coastal areas are already forcing people onto the water. These hubs could provide a more sustainable and safe environment for these communities.
So what I would say about that is, whether or not we arrive at that vision, we need a direction of travel. And remember what I was saying right at the start, we need systems thinking. Of course, we need individual technologies, we need good policy environment, we need an investment structure that puts money behind this, but we need to create systems, and that was a great way to capture it. And this next slide shows a great little energy system in Scotland, up at Orkney, where we'll go through the Scottish Hydrogen and Fuel Cell Association, all the partners that you can see here, a way that hydrogen is being driven, green hydrogen through hydrolysis. We drive hydrogen out of water, we get some hydrogen storage, move it onto the next island and use that hydrogen to power and drive a fleet of hydrogen-powered vehicles. Microcosm, but there is an energy system such as I'm talking about. It needs that vision and it needs the investment to make it happen. Thanks, Sean. Here's the next slide, something that I think many of you will be familiar with, and this is this scaling up activity. Excuse me just a second while I get my own slides going here. You can see with our colleagues in Pale Blue Dot and the Acorn project, this idea of bringing ashore, as you know, 35% of the natural gas in the UK comes ashore at St Fergus, but using steam reforming, stripping out hydrogen, have that complemented by green hydrogen driven by offshore wind resources, and all of a sudden we've got a new industry emerging, hydrogen production and utilisation. And hydrogen not necessarily just for combustion for heating and the likes, but hydrogen for industrial processes, respectively having hydrogen and others combined with other gases to produce new synthetic fuels. So again, here is a system, Aberdeen right at the heart of it. It needs strong industrial leadership, it needs government backing, and we can see then the way that nets in prospectively into the national transmission system to load to some extent or pressurise hydrogen into the existing gas network. So again, here's a system at work, high impact, high cost, but of course you need to go through that stage before you turn these into commercial realities. Thanks, Sean. Let's talk about the Scottish Government a little bit. I've mentioned the UK Government and they're to be commended with their commitments, but the Scottish Government decade-plus commitment to their energy strategy has been very impressive. It's driven, our push to have an energy systems vision. I think that has had a real impact in the UK and beyond. And what we've also seen is us broadening this out into cities. And let's think about cities briefly. Thanks, Sean. Here's the whole systems view. And what we're saying is let's take an integrated approach to heat, to power and transport. And now we have a 50% all energy target by 2030 from renewables. The energy transition is key, and that has to be coupled with our commitment in our climate change plan and having a flexibility to changes in technology. So that is the key here. What are the low regrets investments in energy that are going to be required in any case for any future decarbonised power system? Now, as a grid man, I'm going to say in any model, we're going to have a smart, reconfigurable, low-carbon grid to produce fast charging, to drive electrification of heating, of transport, and others. And clearly, we're going to move towards more offshore wind, and likely, I think, to have a fleet of smaller nuclear reactors and gas-fired coupled with the carbon capture and storage. But remember that bigger picture of bioenergy coupled with CCS and also zero emissions technologies. So we need also a smarter model for local energy provision as well as the centralised stations. Keep going, Sean. And here's the model in Scotland just now. When we think of energy, very often we think immediately about electricity. But electricity only makes up around 22% of the demand for final energy consumption. Blue, not surprisingly, given the week that we've had, that's heat. And we need that energy for heat. A lot of it is, gas-fired. Some of it are off-grid. It's colour gas. Some of it electrification and transport. So you can see the model here. Keep pressing, Sean. Which means in house. Think about your own household. In your household, about 3/4 of your energy requirements comes from space heating and water heating and cooking. So we need to understand what we're trying to do here. Where are the opportunities to decarbonise? Where are opportunities to redesign? Thanks, Sean. And the role of cities. I mentioned earlier, currently half of the world's population are urban based and responsible for 75% of the world's energy consumption. And that's going to increase because currently 80% of the world's greenhouse gases arise in cities. So we need a new vision for cities. We need an integrated plan. We need a systems perspective that couples transport, power, heating, lighting, industrial processes, and this will continue to be the case. So we need that big vision. You saw a little company like Marin having a big vision. Think systems, think about how these things knit together to create the future. And thanks very much. And no booing and hissing from the audience in Aberdeen, please, but I would commend Sustainable Glasgow. I was involved in establishing this about 10 years ago, where Glasgow had and still has this vision about becoming one of the greenest cities in Europe. And the interest in this from the city leadership has emerged very quickly again because of the fact we're hosting COP26 next year. So there's lots of very good demonstration projects underway on transport, on energy efficiency, on using the River Clyde in a more sustainable way, and so it will go. And I'm just going to cycle through these next slides quickly in the interest of time, Sean. So the community energy, I'll simply say that it's important to have our citizens engaged, to get benefit of decarbonisation, but get the commercial benefit as well. And we've got a 2020 target to exceed 500 megawatts of community-owned renewables. Sean, go on to the next slide, please. And examples of this would be, for example, the Garminy Hydro and access on Mull. We're seeing this is community-owned, thick end of a 0.5 megawatt of hydro instigated by the Mull and Iona communities. And profits going into the Waterfall Fund. Again, Sean, please. Another project is Levenmouth. Again, some of you are familiar with this, everything from hydrogen, storage, PV, electrification of transport. There's a demonstration turbine there, which is run by the Offshore Renewable Energy Catapult for research and innovation purposes. Again, Local Energy Scotland involved in that. And looking on to the next slide, on Scottish targets, we can imagine with these community engagements. So petrol and diesel car and van sales phased out by just over 2030, address the mixture that we talked about on that energy mix in Scotland, get the heat demand addressed by as much renewable sources as we can. And 5 years ago, we had about 3/4 of electricity produced by low or zero carbon sources. But in all of this, consumer is key. You remember when I talked about the trilemma, I made it the quadrilemma when I played in the consumer opinion and sentiment. Sean, next slide, please. We can see here we are going to move to electric cars in a major way. We need a big infrastructure again of rapid DC charging. Here are sites that have already been identified in terms of DC chargers, and you can see this growth in the requirement here if we're going to have this rapid phasing out of internal combustion engines and more hybrid and all-electric cars. Thanks, Sean. And here's a vision, and I tip my hat to Scottish Power. Again, it's a cartoonish, but it lets you think about the delivering more customer value. Again, going round clockwise from the top, you imagine the family of the not too distant future will have a domestic EV charging capability. Access, of course, to public EV charging is key to make these things workable. Mobile energy packages where the consumer becomes prosumer and engages in how they buy energy and use energy, including home energy management. Lots more smart appliances, that's that distributed intelligence, not just out in the network and the system, but in our homes and having connected services all the way through to low carbon living. But I just want to give you another historical reference, because unless I buy in, unless you buy in, it won't happen. And let me show a genuine sign on the next slide from Thomas Edison's days when he tried to electrify some homes. That's a genuine plate that Edison had for his customers, because people were used to having the gas mantles and the gas lights. And just to stop people being too worried about it, Edison did say, please don't use a match to light the electric bulb. Simply turn the key in the wall. And you'll also notice, I smile, that they had to reassure them that electrical lighting was in no way harmful to health and not affecting the soundness of sleep. Although if I don't hurry up with my presentation, I'll have you all asleep in a moment. Okay, Sean, keep going. So I'm going to run through this quickly. We have a responsibility to make sure energy is sustainable and invested around the world. So let's look at energy for development. Thanks, Sean. We've talked about the 17 Sustainable Development Goals, critically important for an equitable, inclusive and sustainable planet, with everything from dealing with poverty, access to clean water and energy, and the SDGs should drive a lot of our thinking. Thanks, Sean. Here's an image. Here's the electrified world at night. Look at North America, look at Europe and parts of Asia, and look at how dark we see things in some parts of Africa and other parts of the developing world. This is unfair, it's not sustainable, and we need to think how we deal with it. Sean, next slide. And the idea here is that we've got 1.2 billion people around the world without access to electricity. And you see the distribution here, and with almost 2 billion others that have unreliable access in Nigeria and India, around about 30 blackouts per month. Can you imagine if that happened here? And you can see here this trade-off between energy use, with America way up at the top there, and some of our friends and colleagues in near North Africa and throughout the continent, where there's a big issue there around the trade-off with that, with the Human Development Index. So we need to deal with this. And again, taking a sustainable, taking an empathetic and inclusive way, we should be building more here. So what do we do? Keep cycling here. Thanks, Sean. Let's go to the next slide. So energy access levels, dreadful for health. Candles and kerosene still used. There's a lot of Pico solar products now building to have more distributed solar panels, then building up mini grids and then national grids. So you can see the proxy that I'm making here, the sort of move we've got towards advanced systems for distributed energy. It's precisely the same model we need in developing nations as well. And in many ways, we can have them bottom up, build a grid as opposed to top down, as we've done over the past century. Next, Sean. Just keep going, thanks to the next slide. So bottom up electrification. So here is one of these solar homes, and Strathclyde and other universities with sponsorship are deploying these systems. I have students that go out every year to Malawi and the Gambia doing this. So solar homes, unique homes. Next slide, thanks, Sean. And by doubling up, we can start to interconnect these little systems, and all of a sudden you've got a mini grid. So just hold it there, Sean. So instead of top-down electrification, which is a traditional approach, where we've got large-scale stations, transmission system out into the local area. Next slide, please. What we've got is what I would call swarm electrification, where you've got lots and lots of these little individual units that are set up as mini grids, then they're translated up. We can start pushing the voltage up for transmission efficiency. And all of a sudden, again, we advise the Malawian government that there's lots of international aid goes in, but the international aid seeks to replicate the architectures that we've got in our nation. We should perhaps think again about inversion, which is always a good way to think about problems as engineers and scientists. Invert the problem, get rid of some of the existing constraints. And what you can see here is that in the energy gap, we've got 1 kilowatt hour of energy. In America, that's about 33 kilowatts hours of energy a day. In Malawi, less than a third. Sean, just give us a couple of cycles in that, which means in America, that's what energy consumption looks like. And in our colleagues in Africa, it's here. So final few slides, and then we'll stop for questions. Oil and gas, a big part of the solution here. It's easy to have a pejorative comment about them, but the commitment I hear from colleagues such as Bernard Loney from BP about the commitment to energy transition. We have to drive this. Oil and gas is the investment capability, technical know-how, and they know how to deliver major projects. So next slide, Sean. And that's all about setting it in the context of the energy transition. And thanks to Deirdre Meekie for these slides. Oil and Gas UK is happening now. Oil and gas shouldn't be a spectator. It needs to be in the middle of it, influencing, participating, investing, and creating that future alongside PV, wind, and grid evolution. Next slide. So the proposition's not a loose one. The Oil and Gas Authority, OGA, have produced some very nice material over the past year, envisioning where oil and gas fits in here, whether it's carbon capture and storage, whether it's blue hydrogen, whether it's setting up using oil and gas know-how offshore, the basis for combining offshore wind with the gradual phasing out of oil and gas recovery, but then perhaps doing, as you saw in the Marin slides, doing some conversion out at sea to get ammonia, to get methane, to get hydrogen, and then building up these integrated energy systems. Okay, Sean. And we'll just go through these next ones, Sean. Let me just couple on to keep going, Sean. Go to the plate that's headed up, not just lithium. Okay, just there. So batteries, we've not talked a lot about storage, but storage will be critical, whether it's Elon Musk's power pack or power in the wall pack, and whether it's new lithium ion storage, whether it's new compressed air models, whether it's superconducting magnetic energy storage. Another big area for research, but many of these are now at the higher TRL levels, which will give us this grid scale storage as well as distributed storage, such as in our car, such as in our homes. Okay, and the last couple of slides, nuclear is still here. You've seen the fleet is phasing out in the UK. This is the existing nuclear, which represents about 20% of UK generation. If we're going to the next slide, Sean. Across the world, though, there's over 400 nuclear reactors operating in 30 countries. There's 50 reactors currently being constructed, and the opportunity is to play that into a systems perspective of decarbonising energy supply. And the next slide, Sean, I mentioned advanced modular reactors, which are, and here's another combination, AMRs, typically high temperature. They produce electricity, but they also produce heat. And using that heat for industrial process, you can combine it for the production of hydrogen. However, is society ready for lots of distributed 400 megawatt nuclear stations? We'll see. But the next 5 years, I think we'll see these being developed at pace. And I expect the Energy White Paper next week will talk about a £1 billion nuclear innovation fund over the next few years to try and accelerate the production of small modular reactors and keep the manufacturing as well as the operation here in the UK. Okay, let's just cut to my last two slides, please, Sean. Oh, there they were, in fact, sorry, that was well timed. So final comments. And I would say this, we need big national and international visions here, strong leadership, strong policy that's then can be depended upon, and lots of innovation, vis-a-vis what Lord Weir did in 1926 in setting up the Electricity Supply Act. Digital engagement will turn us from consumers into prosumers, and cities are going to be a big deal, and including keeping an eye on the market disruption. So it's not just about big companies like Scottish Power and SSE. There's lots of what's called disintermediation going on, where there are new actors, including companies such as BP and Shell. But if they are acting together to get that systems perspective to decarbonise, and so be it. Energy trilemma must be resolved, and the quadrilemma with us involved as well as consumers addresses the Stern report urging of how we address climate change. We need a systems architect. Now, I'm an electrical systems engineer. I would say that, wouldn't I? But the new UK government policy is all driven by a systems engineering perspective of how to achieve low carbon. But we need this urgently. And my very last slide, colleagues, is this. Nonetheless, with these challenges, and for all you students out there, as well as the great learning that you've had at Aberdeen and other places, have purpose and apply an entrepreneurial spirit. That's where Edison and Westinghouse and Tesla and Lord Weir and Page, who set up the national grid, they were entrepreneurs. They were engineers and technologists, but they were entrepreneurial. So let's play in that entrepreneurial spirit to address decarbonisation and create companies and industries. We're absolutely in the midst of a historically defining period for the development of energy systems. We don't have the luxury any longer of prevarication. We need to move now at pace to create that 2050 future, and we need to start now. Because energy systems and sensing is accelerating now, like Moore's law. You know, Moore's law is this doubling every 2 years of computing power. We're seeing the same sort of amplification and acceleration in the energy technologies, and there's never been a more exciting time, never been a more challenging time either for power and energy systems. And the last thing I would say, none of this will be done without fantastic talent coming out of our schools, colleges and universities. And this is the sort of big vision. This is the big drive that we need to attract more young people into engineering, science and technology. And with that, I'll stop my lecture. Thank you very much.
Thank you very much. Wonderful. I'm dazzled by your grasp of I would say, strategy and detail. It's just unbelievable how you're able to do it. We have a lot of questions, actually. So let me maybe start with Russell McKenna, who is our professor of energy transition at Aberdeen. So I'm just reading the question. Thank you, Jim, for excellent lecture, giving an exciting and humorous overview of the pressing topic. You listed a lot of important motivation, but in my view, one key aspect was missing there: economics. Cost was and still is one of the key drivers towards the low carbon systems. Maybe I'll stop here, Jim, or you can answer that.
Yeah. It's a great point, and I accept that point completely. So coming to the economics, I mentioned Nick Stern, and I'm sure my colleague knows Nick, who is an economist, happens to be a climate change economist. If we take offshore wind, for example, 5 to 10 years ago, £140 per megawatt hour. Not competitive. However, with the renewable obligation certificates, with the policymakers committing to make this industry come into a commercial basis, with entities such as the Offshore Renewable Energy Catapult driving innovation, with work between the developers such as SSE, Scottish Power, the OEMs. Now what we've got is an offshore wind industry that can strike prices at about £50 per megawatt hour. So what that switch over now is that the economics work, and the same would have been true for, if you look at any technology development, that the cost base at the start of its journey through the TRL levels are not at the commercial or sustainable bit level. But I completely agree with my colleague that trilemma becoming a quadrilemma and beyond. It needs technology, policy, economics and public acceptability to make it work. So I completely agree with you. If the economics don't work, it won't work. The only qualification I'll make there, the economics of getting climate change reversed is even worse. So we need to bear in mind this super level economics of us damaging our planet further, and that's what we need to trade off. But I completely accept, as we introduce new technologies, new systems, the economics ultimately have to play into a marketplace where it's sustainable.
Thank you very much, Jim. Next question is from Ian Funnell, CEO of Hitachi Power Grids. A fantastic lecture, Jim, thanks. As a student of the great R.V. Jones, a fitting tribute. I know you are an electrical engineer, but what is your vision for mechanical energy storage?
Ian, great to hear from you. And Ian has a great vision for offshore electrical grids as well. So now make sure I answer Ian's questions properly, Marion. Ian's question was it mechanical engineering?
Mechanical energy storage, yeah.
Okay. So Ian, the electromechanical integration for me is one can't decouple it. If you think, for example, I remember not so long ago working with Rolls-Royce on superconducting magnetic energy storage devices, which were potentially going to be on aircraft and could have been in other places, critically dependent on mechanical technology, frictionless bearings. Actually, it was magnetic bearings that were keeping the mass away from actual mechanical contact. So needed a lot of mechanical innovation. Flywheels as well, clearly been driven by electromechanical principles, and we have to revisit these technologies now that we've got more advanced materials. And I could have said this throughout my lecture, materials technology is going to be an absolute game changer, whether it's the next generation of power electronics devices, whether it's energy storage and the likes. So flywheels, another big deal. Compressed air storage in, for example, lined mine shafts, again, critically dependent on pumps and valving. I feel as if I owe you an apology. So it's not just electrical engineers that will make a difference, Ian. We do need mechanical engineers as well. So I'm happy to concede that.
Okay. I think somehow we got a lecture instead. I have another question from Professor Ekaterina Pawlowskaja. What is, in your view, is the role of and future of the nuclear industry in Scotland?
It's a good question, and as you mentioned, as George mentioned earlier on, I have the privilege of co-chairing the Scottish Government's Energy Advisory Board with the First Minister. This Scottish Government has been clear throughout their time in office, Marion, that they would not support the building of new nuclear in Scotland just now, and that's their policy position. As an engineer and as someone that actually worked in nuclear power stations as a youngster, I see a very important role for nuclear going forward. So what the Scottish Government has said, and I think it's a good thing to say, is that lifetime extension and the management of the current fleet is important, because it gives us that base load plant that allows us to coordinate and integrate with the offshore wind. But what I think, if we can come up with a credible argument in the coming decades, and it's probably going to take that long, about convincing certain policymakers and parts of the public about safe storage, safe operation, then it's not for me to speak for the Scottish Government, but I would advocate always for an appropriate fuel mix, which would include renewables, wind, onshore and offshore, marine energy as it comes of age and commercially viable, tidal and wave. But I would see in some of the future that we saw in the 10-point plan, small modular reactors would also decarbonise the system, and small modularised reactors, gas with CO2 capture to give us other base load and dispatchable units, a fleet of offshore wind and more onshore wind, and of course the distributed energy. For me, that is the future, and I respect the SNP party's commitment to that. But as an engineer, I would also always be looking for a mix, a set of complementary technologies to do that moderation, and so that we wouldn't get a single point failure, as it were, on a certain technology direction.
Thank you very much, Jim. A couple of more questions, if you don't mind.
Sure.
The question from Steve Cotton, it relates to Northeast. Now some of the oil and gas majors are signaling they are going to attempt to get on board with the energy transition. How do you think this will change the pace and strategy, considering they also need to keep shareholders happy? happy.
Yeah,
it's a very interesting question. Yeah,
it's a great question, Steve. And let me give you an investor argument, then I'll try and give you a technology argument. Internationally now, there is no doubt there's been a switch over from the investor community for a concentration around environment, societal and governance focus, or ESG. And when you get big investors such as BlackRock, the CEO coming out about a year ago saying he would not advise his investment community to put stock into industries that were not committed to sustainability and had a clear plan and role where they made a positive contribution to society. So in many ways, the technology's been there for a long time, some of them for decades. I think the investor sentiment, society's expectation of companies, the need for companies to demonstrate their ESG credentials will be as one of the biggest drivers for the oil and gas industry to move on that transition. And again, I can't speak for the industry, but when I read what Bernard Loney, for example, says, and it's not just him, there are many other senior actors in the oil and gas industry, I welcome that commitment. Now, there's going to be the science and the art of the transition. You know, the International Energy Agency will tell you that we're going to need hydrocarbons for another few decades as we make that migration to a decarbonised future. But we need to start now, and the commitment and the leadership from people such as BP, Shell and others is going to be critical because of the investment headroom that they have, because of the technical skills that they have, and their ability to deliver large-scale projects, and having them doing that in partnership with a Scottish Power and SSE, you know, with small innovative companies, so that lots of the supply chain companies within oil and gas can, I won't say easily, but can move towards that energy transition to capture more commercial opportunity. And that's where I think Aberdeen and the Energy Technology Zone and what Roy McGregor is doing up in NIG with Global Energy, fantastic, pioneering engineers and business people, and oil and gas, I think, is a key role in all of that.
Jim, there's a lot of questions. I don't know how much time do you have. I think I would like to close at that note, but so you have promised to answer the questions which are all, so I will keep you in the account.
Well, is there a final question, Marion?
You can answer one more. What you want?
Sure.
This question was pretty nice to close the basically session, but if you have time, I can pull one or two up to you.
Okay, please go ahead.
Yeah. Okay. So there's one technical one. I know that you are incredible. Just keeping the strategy and technical stuff in the same place. From David Morris Smith. You emphasize distributed generation and decentralization. Does this and the web of cells idea help overcome the black start problem, where the faults cause a cascade of events on the grid that lead to a large-scale blackouts? At the present, we need some large generators to get the system going again. Yeah. Does the move to small-scale but integrated system provide the necessary stability overall?
Yeah, that is a terrific question, David. Thank you for that. So for those that don't know about black start, so black start is a state of readiness that the large electrical power systems must have if there was a major weather event, or if there was some other a collapse in the system that was brought about. Then large power stations might come offline. Energy supply is disrupted, and basically the system goes black. When I was a young engineer, and the utility industry was in public ownership, I had the pleasure of, with many other engineers, playing with the system in the early hours of the morning, shutting down Longannet Power Station and shutting down Hunterston, and then bringing them up, because our colleague is mentioning black start. When the system is dead, you need to build from the base. So, for example, Cruachan Power Station at that point would start up, produce electricity from the pump storage, energize the transmission lines, and then get electricity supply into, for example, the boiler feed pumps at what was Longannet at the time, get those pressurized, get water into the boilers, start up the burners, and over the course of 12 hours or so, start up the large stations again. So black start is a big issue, and I won't go into all the detail, but just now in the UK and in Scotland in particular, the black start time has been lengthening to prospectively, under some challenging scenarios, several days worth of outage across the central belt. So that is disastrous for business. There's an issue there for security and safety. So David, to your point, if we invert that, still recognising we need large-scale centralised generation, if we invert that, the decomposition into this cellular construct where there's solar, wind, good storage, it means that, let's say in my little community here in Ayrshire, there's maybe 12 houses. If each of us had the equivalent of about 20 to 30 kilowatts of power generation and storage, in many ways we could moderate and share between each other. So that little microgrid becomes a much more sustainable and resilient system. The art of the cells is it's not decomposition and then keep them decomposed. By using advanced control, advanced communications and an overarching management system that's maybe driven by some distributed intelligence, these cells can automatically reconfigure after an event so that you can in many ways build up from the bottom. Just to your point, black start is the assumption here is you really need to start things going by getting the big stations in again, and that would ultimately need to be required. But in many ways, by taking that swarm electrification approach, not just in developing countries, but having a swarm approach through that cellular structure, arguably we've got a more resilient, reliable, and steady power supply and energy infrastructure.
Thank you very much. I think we need to close. Jim, fantastic lecture. I think there's so many questions, but I think we have to hold here. Can I ask now Head of School of Engineering, Professor Igor Gus, to close the lecture?
Good evening, everyone, and I have the most pleasant role today to thank everyone. First of all, of course, our distinguished speaker for the fascinating insight into energy systems for the 21st century and our drive for net zero. I would also like to thank Professor George Boyne, our principal, for introducing this event and for always supporting engineering in Aberdeen. Our brilliant team of organizers, led by Professor Virchigroch, everything worked, no technological glitches, which is almost unbelievable. Thank you. And last but not least, the audience. Our joint effort. With our joint effort, we have broken the University of Aberdeen record for such events. As of this morning, more than 400 people registered for this event. So well done to all of us. Thank you for your participation and for excellent questions. And I also would like to invite you. I very much hope we will be able to invite you for the next lecture here in Old Aberdeen in person next year on our beautiful Old Aberdeen campus. With this message in mind, let us hope things will become much better. I would like to wish you all Merry Christmas and happy and prosperous New Year. Keep safe and let us meet again in Old Aberdeen. Thank you.
Thank you very much.
Thank you very much. I enjoyed that. Thank you very much, Marian and Igor. Well done for organising so well. I'll see you soon. Thank you very much.
Thank you, Jim. Wonderful. Yeah.
Bye-bye.
All the best.